guys, in this video we're going to look at radicals. We're going to convert from radical form to exponent form. We're going to simplify some radicals and evaluate some radicals. So the first thing that we're going to look at is how to actually convert from a radical expression into an exponent form. So if you see a radical, so radical meaning like square root, cube root, etc. A square root means what squared will equal that value. A cube root means what to the third power will equal that value, and so forth. So we're going to primarily look at square roots, but you can have the fourth root. For example, the fourth root of 16 is 2, because 2 to the fourth power equals 16. So basically the nth root is just the opposite of the nth power, so, or the inverse operation. So we know that the nth root of a is equal to a to the 1 over nth power. So we're going to be using this idea a lot. This can help us solve equations. It can help us realize what to simplify radical expressions, etc. So the other thing is that if a is raised to a power, and then you're taking the nth root of that, this is actually equal to a to the m over n power. And if you recall the power rule for exponents, if you have a to the m raised to the 1/nth power, so again a to the m being the base, and then you're taking the nth root of that, which would be 1 over n power, the power rule says that we can multiply those exponents. So a to the m times 1 over n, and that's a to the m over n. So that's where this relationship comes from, just kind of a side note there. All right, so we're going to look at a few examples. We're just going to convert between radical form and exponent form. So the first one to look at is the square root of a. If you don't see a number right here, it's understood to be a 2, square root. And I think that's what most of us are familiar with seeing. So this is the square root. So this would just be a to the 1/2 power. Again, that's understood to be a 2 if you don't see anything there. Second example, if we see the fourth root of m, that's equal to the a to the 1/4 power. I'm sorry, not a, but m, since that's our base. I'm still on the previous problem. But the fourth root of m is equal to m to the 1/4 power. Again, using this rule, it's just a to the 1 over n, whatever that root is, and in this case 4. All right, here's another example. Square root of m to the 4th power. All right, so we can look at this as m to the 4th power to the 1/2, because it's the square root, which would be m to the, again, using this power rule, 4 times 1/2 is squared. But we can also look at it just using this rule. Anytime that you see the nth root of a to the m power, or in this case the square root of m to the 4th power, this would equal m to the 4/2 power, which would reduce to m squared. So you can kind of use that as a shortcut, but if you forget, you can write it out like this, where you just take whatever's underneath that radical, raise it to the 1 over whatever the root is, and then simplify using that power rule. Then we have the square root of x cubed. Again, using this rule up here, we would just have x to the 3 over 2 power, or 3/2 power. Again, if you don't see a root there, it's understood to be 2. All right, so that's converting from radicals to exponent form. We're going to look at a few where we convert from exponent to radical. So the first one, if we have x to the 1/5 power, that's going to be equal to the 5th root of x. Again, just using that directly. Number 2, we have y to the 2/3 power. If you notice here, when we look at this formula, m is the power and n is the root. So 2 is the power, 3 is the root. So this is going to be the cube root of y squared. And then the next one, we have a to the 1/4 power, which is equal to, using this, 4 is n, so that's the 4th root of a. All right, and then very last one for converting, we have x to the 7/6. Again, the 6 is the root, 7 is the power, so it's going to be the 6th root of x to the 7th power. And that's it. So like I said, this will come in handy when we're simplifying radical expressions later. So this is a very useful thing. It will also help to solve equations and things like that. So All right, we're going to use this to help us, this idea to help us simplify radical expressions. So our instructions here are to simplify. And I'm going to first look at a very basic example. The answer to this is a. The square root of a squared is a, and I know that because they're inverse operations. Squaring something undoes the square root of something, so these are inverse operations. But you could also look at this using this formula where it's a to the 2 over 2, which is just a to the 1 power, or a. But I know that in the future, like if you take the cube root of x cubed, it'll be x. If you take the fourth root of a to the 4th power, it'll be a, etc., because those powers undo each other. We'll talk about that with solving. All right, next example, we have the square root of a to the 4th. This is similar to what we saw before, but this would, using this rule, it'd be a to the 4 over 2, and then we can reduce that to a squared. Another way that you can look at this, and I'm going to just note this for something that we're going to look at in a little bit, but you could also look at this as a squared times a squared using the product rule for exponents. We know that a squared times a squared, we add those exponents to get a to the 4th. So if I break these up, I know that this is equal to a to the 4th, and then I can see the square, it's really a squared squared times itself. So the square root of a squared squared is just a squared. Again, a little bit excessive for this example, but this is something that kind of gets us thinking about some examples that we'll see in a little while. All right, next example. Square root of 4m to the 6th power. All right, we're going to use this concept up here a little bit that I was mentioning. First thing I want to do is realize that the square root of a times b is equal to the square root of a times the square root of b. This is only true for multiplication and division. We'll see a division in a little bit. But so I can actually break this up into the square root of 4 times the square root of m to the 6th. Now again, using that idea that I was just talking about, I can take this m to the 6th, and I'm just going to leave this as it is right now, but m to the 6th I could write as m squared times m squared times m squared. I'm doing that because this is a square root, and you'll kind of see where I'm going with this. But we have the square root of 4, and then using this rule up here, I'm going to break this up to the square root of m squared times the square root of m squared times the square root of m squared. And then I can actually take the square root of all of these things. So the square root of 4 is 2. Square root of m squared, again, square root of a square, it just cancels out, so you're left with m. Square root of another m squared is m, and square root of another m squared is m. So then if I simplify this, I just get 2m to the 3rd power. So this is useful, again, to look at it kind of for understanding, but if we shortcut, going back to this rule, I can write this as the square root of 4 is 2, and then I can look at this as the square root of m to the 6th. I'm going to go ahead and just write that like this, but then change it to that exponent form. It would be 6 over 2, which again is that 2m to the 3rd power. So there's a couple different ways that you can look at it, but I show you this for understanding. This is the shortcut using this formula. All right, so let's look at a couple more. All right. So we have square root of 16y to the 4th. Now what I'd really like for you guys to be able to do is, like, after you see several of these problems, just look at it and tell what that answer is. The square root of 16, you can treat the 16 separately from the y to the 4th power. Square root of 16 is 4. Square root of y to the 4th would be y squared, because it'd be y to the 4 over 2, which reduces to 2, so exponent's 2. All right, and then here's one that's a little bit different from what we've seen. All right, square root of 50. Perfect squares are numbers that you can take the square root of and get an integer value. So 16 is a perfect square because the square root of 16 is 4. But for example, and then square root of 25 would be 5, so 25 is a perfect square. But a number between 16 and 25, like 20, doesn't have a number, an integer value that can multiply by itself to get 20. So 50 is one of those numbers. It's not a perfect square. The closest perfect square is 49. So we could say, well, this is going to be close to 7 because 7 squared is 49. But I want to get an exact answer for my simplifying here. I don't want to evaluate it. You could type this in your calculator and get a number, but I want to simplify. So what I'm going to do is I'm actually going to find a perfect square that goes into 50, which would be 25. So 25 is a perfect square. Square root of 25 is 5. So I'm going to rewrite this as the square root of 25 times 2, because this is clearly still the same thing. And then I can use this rule up here where I can break it up and say square root of 25 times the square root of 2. And then square root of 25, 5. Square root of 2, I can't take. It's an irrational number. But I'm going to leave this as an exact answer, so I'll leave that radical there. This is the simplified answer to the square root of 50. All right, so anytime that you have a number that you can't take the square root of, if there's a perfect square that goes into that, we can simplify it in this way. All right, here's another example. All right, square root of 80y to the 8th. So I'm going to treat this, again, separately, the square root of 80 and the square root of y to the 8th. So we can kind of write it out like that first, and then treat each one separately. The 80 is not a perfect square, but there is a perfect square that goes into that. Perfect squares, by the way, you could kind of just write them out, like 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 36, 49, 64, 81, 100, and these are just, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared. So these are what are called perfect squares. So this is not a perfect square, but we have a perfect square that goes into that. You might be thinking 4 goes into it. That's true, but it's not the highest number. If you did 4, you'd have 4 and 20, but then you'd still have 20 would have another factor of 4, so you'd have to simplify it more. So 16 actually goes into 80, and it's going to be the number that we want to use. So we'll write that as 16 times 5, and then y to the 8th, we'll deal with that in a minute. Square root of 16 is 4, so I can pull that out of the radical because I'm actually taking the square root of 16. Square root of 5, don't know, it's an irrational number, so that stays under there. And then over here we have the square root of y to the 8th, which again is y to the 8 over 2 using this rule. And then we can simplify that to y to the 4th. Now notice this is not under a radical anymore, so I can rearrange this and bring that out front as 4y to the 4th times the square root of 5. Another way to look at this is sometimes, again, as you get more comfortable with this, write it like this. I can write it like that. And then just bring out everything that you can. So square root of 16 would be 4. Square root of 5 I can't do, so I'm going to leave that under the radical. And then square root of y to the 8th. What do you square to get y to the 8th? Y to the 4th. So you are actually taking the square root of that, so you bring it out, and that would be your final answer. So again, just a couple of different ways to look at that. All right, so a few more of these. All right. So what happens if you have something like this? Square root of m to the 3rd power. If we want to simplify this, we could rewrite it in exponential form like we did at the beginning of this video, but I want to simplify it. I want to get it down in the simplest form, take out what I can from the radical, just like we did in these previous problems. So what I'm going to do is I'm going to actually rewrite this as square root of m squared times m. Because while this isn't a perfect square, just like with the 50 wasn't a perfect square, but I knew that 25 was, so I broke it up into that product. I'm going to break it up into a product where one of those factors does have a square root, or we can take the square root of it. So the square root of m squared, remember, is just m. Square root of m, can't do anything with that. But so I can, however, just write that as square root of m squared times the square root, square root of m. And again, the square root of m squared, like we saw before, is just m. And then the square root of m, can't do anything with that. So m times the square root of m is the simplified form for that. All right, here's another example. x to the 23rd power. All right, 23, and you might be kind of catching on to the fact that if it's a square root, then this needs to be an even number for it to work out, because you're dividing by 2 if you're looking at this rule. So 23 doesn't divide 2 evenly, but the next highest number, 22, does. So we're going to rewrite this as the square root of x to the 22nd power times x. Square root of x to the 22nd, we can write that as x to the 22 over 2. And then the square root of x, I can't rewrite that. It would be x to the 1/2, but we can leave it in radical form. We're just simplifying. So this would be x to the 11th power times the square root of x. And that is completely simplified there and left in radical form. Again, you could simplify it by writing it in, in this form, but that would be rewriting. So just pay attention to what your instructions are asking you to do. If it's asking you to rewrite it in exponential form versus simplify and leave in simplest radical form. Okay, so we're going to look at just a couple more things with radicals. All right, first thing is if you want to evaluate. So evaluate just means you almost kind of see what it's asking. The word value is in that, so we're trying to come up with the value for this. So we want to evaluate f of x equals cube root of y plus 11 for y equals negative 27. All right, so when you evaluate, that means you want to take that value in, plug it in, and see what you get. And this actually, I realize the function of x should have an x, not a y. Sorry guys, I had wrong in my notes. So I want to find f of negative 27. I'm going to plug this negative 27 in there. So f of negative 27, and this is just function notation where f is a function of x, so we're now evaluating, we're plugging that negative 27 in for x. So this does not mean f times negative 27, it's function notation. And we'll talk about that more later. But we're going to plug this in. So cube root of negative 27 plus 11. Cube root of negative 27, that means what times itself 3 times equals negative 27. With square roots, and this is an important thing to note, square root, if you're looking for principal square roots, which principal is the positive value, and we'll talk about imaginary numbers in a minute, but real solutions here, if you ask you the square root of a negative 4, nothing times itself will equal a negative 4. 2 times 2 equals 4, and negative 2 times negative 2 equals 4, but nothing times itself will equal a negative number. So square root of a negative, there's no solution. But with cubes, you can multiply. You could have a negative times a negative times a negative, which would equal a negative. So this will work. So you're asking yourself, what can you multiply 3 times by itself to equal negative 27? And that would be a negative 3. So, and you could type this in your calculator too, just square root, or cube root rather, of negative 27. Or you could put in the parentheses, negative 27 to the 1/3 power. Sometimes some of your calculators, you might not have the capability to do a cube root, but you could convert it to a power. So it's useful there. So this would give you negative 3 plus 11, which is 8, and that's your answer. So if you're asked to evaluate, just consider again, if it's an even power, it needs to be a positive number. If it's an odd power, then it doesn't matter. And then also that key word evaluate means find the value, so you're plugging it in. We're going to look at a couple other things, and I've kind of alluded to this previously in this video, but if you have the product, we want to multiply this and then simplify as much as we can. So remember, with the product, we're kind of working backwards from here. We bring it together under one radical, so this would be the square root of 48 a to the 4th. Remember, you add those exponents, it's understood to have a 1. So we're just bringing this under one radical. If this was an addition, this would not work. They would have to be like terms. But with multiplication, you can bring it under one radical. Square root of 48, don't know. But we do know that there is a perfect square. Never raised them now, but perfect square, 16 goes into 48. 16 times 3 equals 48. and then I'll write that as a to the fourth. So like the previous problems, we can then reduce. Square root of 16 is 4. Can't take the square root of 3. Square root of a to the fourth is a squared, so 4 divided by 2. And then I'm left, I took the square root of that, so I brought it out, and then I'm left with that 3 still underneath the radical. So anything that you didn't actually take the square root of, it needs to stay underneath that radical. All right, so that is simplifying. With addition and subtraction, they have to be like terms. So it has to be a like radical to be able to solve. So like you could take the square root of 2 plus the square root of 2 is equal to 2 square roots of 2. So multiplication you can combine, but addition and subtraction does not work like that. It has to be like terms, just like if it was an x. Instead of, x plus x is 2x. So if you had, again, square root of 2 plus square root of 2 equals 2 square roots of 2. All right, so here's an example of this. We just want to add 3 square roots of 5 plus square root of 5. So there's 3 of them. I'm adding another one of them. There's understood to be a 1 out there. So that gives me 4 of them. So and the same thing with subtraction. You just want to make sure that that you have like factors. So like if you had the square root of 3 minus 2 square roots of 2, nothing we can do with that because they're not like radicals. It would have to be the same, just like with like terms. All right, rationalizing the denominator. So when you have the square root of a non-perfect square, so like the square root of 50, where you end up with the square root of 2 in your final answer when you reduce it, that's an irrational number. We don't like having irrational numbers in the denominator ever. And this is something that becomes, as you get farther in math, you can see like you might have fractions that you have to do further operations with, and having that radical in the denominator will not be pretty. It will make it really messy. So we just want to get rid of it in the denominator altogether. So what this is called is rationalizing the denominator. So let's say that you had 3 divided by the square root of 5. That square root of 5, that's irrational. We don't want square roots in the denominator, period. So what I'm going to do is I'm going to get rid of that. The only way I can get rid of that in the denominator is to multiply it by something that will get rid of it. But if I multiply something in the denominator, I have to do the same thing in the numerator. Because remember, if you multiply the same thing in the numerator and denominator, it's like multiplying by 1. If you think about a square root, what gets rid of a square root? Squaring it. So what I'm going to do is I'm going to multiply this by itself. So we've got the square root of 5. But if I multiply the denominator by square root of 5, I need to do the same thing in the numerator. All right, and the reason is, again, this is just equal to 1. Multiplying by 1 doesn't change the value of that initial. So multiplying straight across, we'll get 3 times the square root of 5. Over square root of 5 times square root of 5 is the square root of 25, which is just 5. So if you recognize that if you multiply by square root by itself, it's squaring it, so it will undo the square root. So that's 3 square roots of 5 over 5. There are some cases where you might be able to then simplify this. 3 over 5, that doesn't simplify. We don't have a like factor, but just keep that in mind. All right, so moving on. So I mentioned that the inverse operation of square root is to square. So what we're going to look at is solving some problems where we're getting rid of that radical in the problem, so radical equations. So we're going to solve, I have the square root of x plus 3 equals 5. I have everything over on this left side is I'm taking the square root of, and I do not want the square root. I want to find out what x is, so I need to get rid of that square root. I can't get rid of the 3 yet because that's underneath that radical, so I need to get rid of the radical first. So to do that, the opposite of taking the square root is to square it. So that's going to square, we'll get rid of that square root and leave me with x plus 3 equals, and then 5 squared is 25. Now I can get rid of that 3 to get x by itself. So I'm going to subtract 3, and that leaves me with x equals 22. And that's my answer. Okay, so looking at a second example, I've got up here 8 plus the square root of y minus 1 equals 15. On this one, just the difference here is that the square root is not isolated. We have this 8 on the outside and it's plus 8, so I can get rid of this first and subtract 8 from both sides. And that's going to give me the square root of y minus 1 equals 7. And then I'm going to square both sides to get rid of that radical because it is now by itself. And then that will leave me with y minus 1 equals 49. And then just add that 1 to both sides. And we will get y equals 50. So that is our answer. And you could go back and plug this into 50 minus 1 is 49, square root of 49 is 7, plus the 8 is 15. All right. The next thing, and this is the last thing, if you have the square root of negative 1, I mentioned that you can't take the square root of a negative number. And that is true in order to get a real number. But there are such things as imaginary numbers. So an imaginary number is just I. And I is defined as the square root of negative 1. So the square root of a negative 1 can be represented with this I, which is an imaginary unit. So if we want to take the square root of negative 25, we can use this idea up here again and rewrite this as negative 1 square root of negative 1 times square root of 25. Again, we know this is the same as what we started with, and then this is just square root of negative 1 is I, and square root of 25 is 5. Typically we see this written as 5i. So another example of that, if you have square root of negative 144, and this is something again that you might be able to just start looking at and tell. There's a negative here, so it's going to be an I. The square root of 144 is 12, so you just get 12i. And then last example, if you have the square root of negative 23, we can't take the square root of negative 23. It is a radical that is not, the 23 is not a perfect square, so we just need to rewrite this as square root of negative 1 times square root of 23, which is I times the square root of 23. Just like those other problems, we can't take the square root of it, so it just stays underneath that radical. And there's no perfect square that goes into 23. It's a prime number. All right, so that's an overview on radicals. And that should cover this unit. All right.